Today we are going to learn Unit 1, Lesson 3, Polynomial Functions. Learning goals for today include understanding the definition of polynomial function and related terms such as the degree, leading coefficient, constant, zeros, orders of zeros, local and global optimum, etc. Determine if a given function is a polynomial function. Understanding key features of the graphs of polynomial functions. Sketch the corresponding graph given the expression of a polynomial function. Write an expression for a polynomial function given its graph. Write an expression for a polynomial function given its zeros with orders and a point on the graph. And analyze the symmetry of a given polynomial function. All right, so we break this lesson into the following parts. First, we'll have a look at the definition of polynomial expression and polynomial functions. And then we'll have a look at graphs and properties of polynomial functions. Then polynomial function in a factored form. And then we're trying to sketch the graph of a given polynomial function. And then we'll learn how to write an expression for a polynomial function give its graph. Then analyze the symmetry of a given polynomial function, and we will also learn what are the families of polynomial functions. Okay, first of all, let's have a look at the definition of polynomial expression and polynomial function. So a polynomial expression is an expression of the form an times x to the power of n all the way down to a1 times x plus a0, where a is a whole number, where n is a whole number. Okay, whole number means 0, 1, 2, 3, 4, etc. And x is a variable. The coefficients a0, a1 to an are real numbers. The degree is defined as the exponent of the greatest power of n. And an, the coefficient of the greatest power of n, is the leading coefficient. And a0, the term without a variable, is called the constant term. So a polynomial function has the form fx equals an times x to the power of n plus an minus 1 times x to the power of n all the way down to a1 x plus a0. Understand? This is the definition of polynomial expressions. And I'll give you some examples down here. For example, the following functions are all polynomial functions. First one, fx equals 4x cubed plus 5x squared plus 2x plus 1. This is a polynomial function with a degree of 3, right? Because the greatest power of x is 3 here, and the leading coefficient is 4. Second, fx equals 2x cubed plus 3x minus 1. This is also a polynomial function with a degree of 3 and leading coefficient 2. Next, fx equals 2x squared. This is a polynomial function with a degree of 2 and leading coefficient 2. Last, fx equals 5. This is also can be treated as a polynomial function. The greatest power of x is 0, so the degree is 0. The leading coefficient and the constant term are both 5. Okay, all right, let's do a practice. Determine which functions are polynomials. Justify your answer. State the degree and leading coefficient of each polynomial function. I'll give you 1 minute to think about this question, okay? All right, let's have a look at the solutions together. So first function. This is a trigonometric function, not a polynomial function, because it does not comply with the definition of the polynomial function, right? We'll learn trigonometric function in the following unit. Second, this is a polynomial function of degree 4. The leading coefficient, sorry, I missed a minus here, minus sign here. The leading coefficient is -2. Next, this is also a polynomial function with degree 3. The leading coefficient is 1. The last function is 3 raised to the power of x. So this time the x is in the position of exponent, not the base. So this is not a polynomial function because the base is a number, not the variable, right? So by definition, this is not a polynomial function. This is actually called exponential function. We'll be learning this in unit 3. Okay, next, let's have a look at the graphs and properties of polynomial functions. First, let's have a look at key features of graphs of polynomial functions with odd degree. That means the greatest order of the polynomial function is odd, right? Okay, first of all, if the leading coefficient is positive. If the leading coefficient is positive, the graph extends from the quadrant 3 to quadrant 1, similar to the graph of y equals x. For example, for the polynomial function y equals x cubed plus twice of x squared minus 3x minus 1, it has a graph like the red curve shown here. Okay, so when the leading coefficient is positive, now the leading coefficient here is 1, right? When the leading coefficient is positive and the degree is odd, the function will look like this. Why? Because when x approaches positive infinity, y also approaches positive infinity, right? And when x approaches negative infinity, y also approaches negative infinity, because the largest degree has the most significant influence on the whole value of the function. So the whole trend of the function is to extend from the third quadrant to the first quadrant. Understand? Please remember this pattern. And next, if the leading coefficient is negative, the graph extends from quadrant 2 to quadrant 4, similar to the graph of y equals minus x. So for example, we have a polynomial function y equals minus x cubed plus x squared plus 6x minus 4. So this time, as the largest degree has most significant influence to the function, so when x approaches positive infinity, y should approaches negative infinity, right? And when x approaches negative infinity, because there is a minus sign in front of x, so this time y should approaches positive infinity, right? So the whole trend of this function should be extending from quadrant 2 to quadrant 4. Okay, also please remember this pattern when the degree is odd and the leading coefficient is negative. So in the summary, the whole pattern of the function depends on the degree and the leading coefficient, right? All right, next, odd function polynomials have at least one x-intercept and up to a maximum of n x-intercepts, where n is a degree of the function. And next, the domain of all odd degree polynomials is the whole set of the real numbers. and the range is also the whole set of the real numbers. Odd degree functions have no maximum point and no minimum point because the function can extend indefinitely to positive infinity and to negative infinity, right? Next, odd degree polynomials may have point symmetry. For example, y equals x cubed. This function will look like this, right? So this function has point symmetry about the origin. Okay, let's see two examples here. First example, suppose we have a function here, y equals 2x to power of 5 minus 4 times x to the power of 4 plus 5 times x cubed minus 6x squared plus x plus 1. So first of all, this function has an odd degree, right? For odd degree function, for odd degree polynomial function, the function is either extending from third to first quadrant or from second to fourth quadrant, right? And note that the leading coefficient is 2. So the function should extend from the third to the first quadrant, right? And if we plot this function in the calculator, it will have a graph look like this. Okay, next, consider the function y equals minus 4x cubed plus 2x squared minus x plus 5. This function has a degree of 3, which is odd. So this function also either extend from third to first or from second to fourth, right? And considering that the leading coefficient is negative, so this function should look like this, extending from the second to the fourth quadrant. Understand? So the whole trend of the function depends on the parity of the degree and the leading coefficient. Okay, next, let's have a look at if the function has an even degree, what will happen? So these are the key features of graphs of polynomial functions with even degrees. First, let's have a look at if the positive leading coefficient exists in the polynomial function. Okay, if the leading coefficient is positive, the graph extends from the quadrant 2 to quadrant 1. That means it will look like something like this, right? The range is y belongs to the real set of R, and y should be greater than or equal to a, right? Where a is the minimum value of the function. An even degree polynomial with a positive leading coefficient will have at least one minimum point. All right, for example, let's have a look at this function. The degree of this function is 4, right? Which is even, and the leading coefficient is 1, which is positive. So this function will have a pattern extending from the second quadrant to the first quadrant. Why? Because as we have discussed, the greatest power of x here has the most significant influence on the whole values, right? So when x approaches positive infinity, y should also approaches positive infinity, which corresponds to the extending in the first quadrant, right? And when x approaches negative infinity, note that 4 is even. So when x extends to the next negative infinity, y should also extend to the positive infinity. So that's corresponding to the extending in the second quadrant, right? Okay, next, if the leading coefficient is negative, the graph extends from quadrant 3 to quadrant 4, which will look like this. The range is y belongs to the whole set of R except that y can only be the values that is smaller than a or equal to a, where a is the maximum value of the function. An even degree polynomial with a negative leading coefficient will have at least one maximum point. So for example, this is called a maximum point. Okay. For example, let's have a look at this function here. The degree is 4, which is even, right? For an even function, it will either look like this or look like this, right? Extending from the second to the fourth, or from the third to fourth. So now let's consider the leading coefficient. This time the leading coefficient is negative. So that means when x extends to the positive infinity, y should be approaching negative infinity, which corresponds to the extending in the fourth quadrant here, right? And when x extends to negative infinity, because x to an even power, that means y should be approaching negative infinity, positive infinity, but there is a negative sign here. That means when x approaches negative infinity, y should also approaches negative infinity, which corresponds to the extending in the third quadrant here, right? So the whole trend of this function, when the degree is even and leading coefficient is negative, should look like this, right? Okay, and even degree polynomials may have from 0 to a maximum of n x-intercepts, where n is a degree of the function. The domain of all even degree polynomials is x belongs to the whole set of R. And even degree polynomials may have line symmetry. For example, y equals x squared. Its graph look like this, right? And this graph have line symmetry against the y-axis, right? Okay, let's have a look at two examples. So first example, as you can see here, the leading the degree of the polynomial is 6, which is even, right? Leading coefficient here is 1, which is a positive number. So according to the features we have discussed, first, when the degree is even, the function will look like this or this, right? And when the leading coefficient is positive, the function will look like this, extending from the second to the first quadrant, right? Next, let's have a look at the second example. First, the degree is 4, which is even, right? So the function will look like this or this. Next, consider the leading coefficient is -7, which is negative, right? Negative leading coefficient with even degree will, so the function will have a pattern like this, extending from the third to the fourth quadrant, right? Okay, now let's consider some other related concepts. What are local minimum, local maximum, global maximum, and global minimum? So according to the definition, the point x fx is a local minimum, is a local maximum if there is an interval a, b with when x is greater than a and less than b. And fx is greater than or equal to fz for every z in the interval a, b. This is the definition of local maximum. So intuitively, if a function looks like this point here is called a local maximum, right? And by definition, the point x fx is called local minimum if there is an interval a, b with x greater than a, less than b, and fx is smaller than or equal to fz for every z in this interval. So intuitively, if you have a function like this, intuitively this point is called the local minimum, right? Okay, so sometimes we also use the term local optimum to denote either a local minimum or local maximum. Understand? Okay. In contrast, global maximum and global minimum means for every x in the domain, this point, if this point is the absolute minimum point, then this point is called global minimum. And if this point is the absolute maximum point of in the whole domain, and this point is called global maximum. Understand? And sometimes if you don't specify the term global here, for example, if a question asks you to find only the maximum, this means the global maximum, right? If you want to find the local maximum, you need to specify the term local here, right? Without the term local or global, by default, the maximum means global maximum, or the term minimum means global minimum. Understand? Okay, for example, let's consider the graph of the function here. We have a local maximum here, right? Because there is an interval. In this interval, x is a maximum point in this interval. So this is a local maximum in this interval. And there is another local maximum here. Also, this point is a global maximum in the whole domain, right? And here you have a local minimum. And for the global minimum in this function, there is no global minimum because this function extends indefinitely to the direction all the way to the negative infinity, right? So there is no global minimum, or we can call it the global minimum is negative infinity. Okay, so I put a note here. Actually, calculus can be used to find the exact minimum and minimum using derivatives. You can dig deeper in the course MCV4U or in your future university studies. Okay, so we'll not talk about too much about this. As long as you have an intuitive feeling, you'll be okay in this course. Okay, let's do a practice. Considering the key features of polynomial functions, match each function with its graph, state the number of x-intercepts and number of maximum and minimum points, and the number of local maximum and local minimum points for the graph of each function. So note that if we don't specify whether it's local or global, by default, maximum and minimum means global maximum and global minimum, okay? All right, I'll give you 2 minutes to think about this question. All right, let's have a look at the solutions together. So first of all, let's consider the first one. The degree is odd and leading coefficient is positive, right? Degree is odd means the function is either look like this or this, right? And when the leading coefficient is positive, so the function will look like this, extending from the third to the first quadrant. That corresponds to the graph in, that corresponds to the fourth graph, right? And the number of intercepts. Intercepts is the intersection point between this graph and the x-axis, right? So there are one, two, three x-intercepts, right? And global maximum, no global maximum or minimum. And there is a local maximum and local minimum, right? Okay, next B. Degree is even. Even degree has a pattern like this, right? A pattern like this or this. And the leading coefficient is -1. That means this function will have a pattern like this, right? Extending from the third to the fourth quadrant, which corresponds to the first graph. And of course, there is no global minimum or global maximum because it extends indefinitely to both sides. There does exist a local maximum. Oh, sorry. There is no global minimum because it extends indefinitely to the negative infinity, right? But there is a global maximum, which is this point. This is called global maximum. Also, this point is also a local minimum, local maximum. And there is also a local maximum here and a local minimum here, right? Okay, the third function. The degree is odd. For an odd function, it's whether have a pattern like this or this, right? And let's consider the leading coefficient. When leading coefficient is negative, this function have a pattern like this, which corresponds to the third graph. And in this graph, there is no global maximum or global minimum. It only has a local minimum here, local maximum here, local minimum here, and local maximum here, right? Okay, last function, the degree is even. So it either has a pattern like this or a pattern like this, right? And the leading coefficient here is positive, so it will have a pattern like this, which corresponds to the second graph. And there is a global minimum here or here, right? Seems that these two values are equal. There is no global maximum. Okay, there does have a local maximum here. And the two global minimum here are also local minimum, right? Okay. Actually, this question checks you the concept, checks your understanding to the concept of maximum, minimum, x-intercept, and also checks you the understanding of the features of the polynomials. Okay. All right, let's see some other features of the graphs of polynomial functions. The following features are applicable to both odd and even degrees. So first, a polynomial function of degree n, where n is a whole number greater than 1, may have at most n-1 local minimum and local maximum points. For any polynomial function of degree n, the n's differences are equal or constant, have the same sign as the leading coefficient, and are equal to a times n times n minus 1 all the way down to 1, where a is the leading coefficient. Okay, this is another important feature of the graphs of the polynomial functions. So note that we always denote the multiplication from n to 1 as n factorial. So this reads as n factorial, which means multiplication from 1 to n. Okay. Well, actually, the proof of these two properties are related. Are also related to calculus, which you can learn in the course MCV for you. So we're not gonna prove this. We're not gonna prove this here. Okay. All right. Let's see an example. The following table of values represents a polynomial function. Use finite differences. Finite differences means this property. Okay, for any polynomial function of degree n, the n's differences are equal or constant, have the same sign as the leading coefficient, and are equal to a times n factorial, where a is the leading coefficient. Okay, let's see a concrete example here. All right, use finite differences to determine first the degree of the polynomial function, second the sign of the leading coefficient, and the value of the leading coefficient. Okay, I'll show you how to do this. So first of all, let's calculate the first difference. Okay, according to the property, if the function has a degree of n, then the nth difference would be constant, right? So let's calculate the first difference. So note that the distance between each value of x here are equal to 1, right? So we can calculate the first difference by just subtract the two numbers y here. So first difference, minus 12 minus 36 is 24, right? And then minus 2 minus 12 is 10. And then 0 minus 2 is 2. 0 minus 0 is 0. 4 minus 0 is 4. Then 18 minus 4 is 14. 48 minus 18 is 30, right? So these are the first difference of this function. Now we can calculate the second difference based on the first difference. So second difference, first we have 10 minus 24, which is minus 14. Next we have 2 minus 10, which is minus 8. Next, 0 minus 2 is minus 2. And then next, 4 minus 0 is 4. 14 minus 4 is 10. And 30 minus 14 is 16, right? And based on the second difference, we can calculate the third difference. Third differences are, okay, first, minus 14 minus 8 is minus 6, right? Then minus 2 minus 8 is also minus 6. This should be positive, right? Because minus 8 minus 14 equals positive 6. And minus 2 minus 8 is positive 6. Sorry about that. And 4 minus 2 is also positive 6. 10 minus 4 is also positive 6. 16 minus 10 is also positive 6, right? So as you can see here, the third difference is already constant, is a constant number, right? So that means the degree of the polynomial must be 3, right? Because according to the features here, if the degree is n, then the nth degree will be constant, right? So as we have calculated here, the third difference are constants. So this polynomial must have a degree of 3. Okay, next, the sign of the leading coefficient is positive. because the signs of the leading coefficient and the signs of the nth difference are the same, right? Okay, next, the value of the leading coefficient. Okay, the value of the leading coefficient times n factorial equals to the constant difference, right? The constant difference is 6. And we also know that n equals 3, right? So that means a times 3 factorial equals 6, right? And we know that 3 factorial is a multiplication from 3 all the way down to 1. So in this way, we can calculate that a equals 1. That means the leading coefficient is 1. Understand? Okay, a clear, nicer writing of the solution is illustrated here. You can read it after the class. All right. Okay, so now let's do a practice. This time you need to solve this question by yourself. Okay, following the same method I have shown you in our previous slides. I'll give you 2 minutes to solve it. All right, let's have a look at the solutions together. Okay, so first of all, follow the same method. We can calculate its first differences, second differences, third differences, all the way down to the fourth differences, and find that when calculating its fourth differences, the differences are equal and constant, right? So that means the degree of the polynomial must be 4, right? Also, the leading coefficient has a negative leading coefficient because minus 24 here has a negative sign, right? And also we can calculate the value of the leading coefficient by let A denote the leading coefficient, and then we know A times n factorial equals the constant differences, which is minus 24, right? So A times 4 factorial equals minus 24. We know that 4 factorial is actually 4 times 3 times 2 times 1, which is minus 24. And then we can solve that the leading coefficient is minus 1. right? Understand? Okay, so next let's have a look at polynomial function in a factored form. Polynomial functions can be written in expanded form or in a factored form. Here I made two tables to compare these two forms. First table here is a expanded form. Expanded form means that you have sums and differences of different terms. So each of these is called a term. Understand? And for the first term, we always put the term with the largest number of exponent in the front. And this number here is called the degree, right? We have already learned this. The degree of the polynomial is the largest exponent of x, right? And correspondingly, the coefficient of the largest term, the term with largest order here, is called the leading coefficient. And the last term here with no variable x is called the constant term, right? For example, fx equals x squared minus 1. This polynomial is in an expanded form, okay? On the other hand, factored form of polynomial means it is written as a product of its factors. So these are called factors, right? Not terms, but factors this time. And the coefficient here is called the stretch factor. And for each orders of the zeros, okay, this is called zeros, right? And for each order, for each zero, there might be an order. So P1, P2, Pn are called orders of the zeros, right? For example, if we have a function fx equals x plus 1 times x minus 1, this polynomial is in a factored form, right? It has zeros, x equals 1 and x equals minus 1. And both of the two zeros have orders of just 1, right? Because the exponent of these two terms, these two factors are both 1. Okay. All right. Now let's have a look at orders of zeros in a polynomial function. Suppose a polynomial function can be expressed in this form. If a polynomial has a factor x minus x1 that is repeated p1 times, then x equals x1 is a zero of order p1. Okay, p1 here is called the order of that zero. The graph of a polynomial function changes sign from positive to negative or from negative to positive at zeros that are of odd order, but does not change sign at zeros that are of even order. Okay, I'll set an example. So what does this sentence? What does the statement mean here? So let's look at an example. Suppose we have a function y equals x minus 1 squared multiplied by x plus 2. So there are two factors, right? First factor is x minus 1 with an order 2, right? And second factor is x plus 2. So also we call x equals 1 is a zero with order 2, right? And x equals minus 2 is a zero with order 1. So the statement on the left says for zeros with even order, for example, 0, 1 here, we have already discussed that this zero has order 1, has order 2, right? x equals 1 is a 0 of order 2. 2 is an even number, right? So according to the statement on the left, the sign of the function does not change at this x-intercept, right? But remains positive. On the other hand, let's have a look at the other 0. So when x is minus 2, the function is 0. So x equals minus 2 is a 0 of order 1, right? As you can see here, it's a 0 of order 1. And the sign of the function changes from negative to positive at this intercept, right? So whether it changes from negative or from positive to negative, we need to consider this in conjunction with the overall trend of this function, right? Suppose, for example, for the same function, we know that if we expand this function, we have a leading coefficient equals 1, which is positive, right? And the degree of this function, which is the largest order of x, would be 3, right? Because you have 2x here, 1x here. So the largest order would be 3. So the degree would be 3, right? And according to our analysis in previous slides, if we have a degree of an odd number, this function will look like this or this, right? And then let's have a look at the leading coefficient. When the leading coefficient is positive, the function must look like this, right? So overall, the function would look like this. And also we know that the function has a 0 of minus 2 and 0 of 1. So overall, the function will look like this. And at the 0 of minus 2, it has an order of 1. So it must change direction here, right? And for the other 0, x equals 1 because it has an order of 2. So the function does not change direction here. Instead, it will bounce back, right? So overall, the function will have this pattern. Understand? Okay, now let's have a look at how we can use these features to sketch the graph of a polynomial function. Okay. So basically, there are two types of polynomial function. First type, if the polynomial function is a general power function, for example, y equals x squared, this is actually also a general power function, right? Or a transformed general power function, which we have learned in Unit 1, Lesson 1, right? For example, y equals twice of x minus 3 squared plus 4, right? This is a transformed general power function. Then we can sketch its graph by just analyzing the property of the underlying general power function, right? Which we have already done in Lesson 1 of Unit 1. And for the other type, more generally, for polynomial functions, more general, well, for more general polynomial functions, we can use the following table to organize information about the function. And then considering the properties we have learned in this lesson, use the information to sketch its graph, right? So first of all, for a given function of a polynomial, for a given expression of the polynomial functions, first of all, we need to gather these informations, right? And based on this information, we can sketch its graph, right? So degree, this is by definition. Check the largest order of the variable x. Leading coefficient, also by definition, you need to check it by yourself. And behavior is when x approaches negative or positive infinity, how does the overall function changes? Zeros and x-intercepts, this usually involves factoring the polynomial function, which we will explore in the next lesson. So for this lesson, we can only deal with some simple cases or the expression in a factored form, right? For more complex cases, we'll explore in the next lesson. Okay, and then y-intercept, right? Okay, so let's see an example. Here is an example. Sketch a graph of y equals 4 times 3 times x plus 2 raised to the fourth minus 6. This is actually can be treated as step 1, right? Because we have already learned this. This is actually can be obtained by transforming the original function, which is y equals x to the fourth, right? And this factor corresponds to a vertical stretch of 4. And this factor here corresponds to a horizontal compression by a factor of 1/3. And this factor here means a horizontal translation to the left by a factor of 2, right? And the last factor here means a vertical translation down by 6 units. So we can just transform this function using these transformations to get the new function, right? And after the transformation, usually we'll need to clearly label all the x and y intercepts as well as the vertex if applicable, right? Okay, next let's have a look at the second type. For example, if we have a more general polynomial function like this in a factored form. So first of all, we need to gather all the information here, right? So degree. Okay, if we expand this function in an expanded form, we can see that there are 2x here, 1x here. So if we multiply them all together, the largest order must be 3. So the degree of the function is 3, right? Degree is 3. Leading coefficient. It also can be easily seen that the leading coefficient is -2, right? Because when you expand everything, the largest term, the largest order, the term with the largest order is x3, right? Times the -2 here. So the leading coefficient must be -2, right? Okay, so let's put -2 here. And behavior. And behavior depends on the degree of the function, right? So as we have discussed, the degree of the function is an even number. So this function will have either a pattern like this or a pattern like this, right? And because the leading coefficient is minus, so that means it must have a pattern like this, not this, right? So the pattern of the function depends on the leading coefficient as well as the parity of the degree. So that means the function should extend from second to fourth quadrant. Okay, zeros and intercepts. It has 2 zeros, right? First, it has 0 of x equals 1 with order 2, right? If the order is greater than 1, usually we'll specify its order. And another 0 is x equals -2. If the order is 1, usually you can leave this blank. By default, the order is 1, okay? And y-intercept. To calculate the y-intercept, we should let x be 0, right? If x is 0, y equals -2 times 1 times 3. Times 2, which is -4. So the y-intercept is 0, -4. And then if we have all the information here, we can sketch this graph, right? So first of all, we know that this function has 2 zeros. 1 0 is -2, so it must cross this point. And another 0 is x equals 1. Also, it must pass this point. And this function has a pattern like this, right? Extending from from second to fourth quadrant. And note that the 0x being -2 has an even order, right? Because order 1 is the 0 of x being -2 has an odd order, right? Because order 1 is an odd number. So the function should look like this. It will cross this point, because if the 0 has an odd order, the function should change signs at this 0, right? And extend all the way to the other 0, 1. And note that the 0, 1, 0x equals 1 has order 2. Order 2 is an even number, right? So if a 0 has an even order, this function does not change sign here. So it bounces back and extends all the way to the fourth quadrant. So basically it has a sketch of this, right? So if we plot this on a Cartesian plane, this is a graph of this function, which is corresponding to our analysis in the draft here, right? And usually we'll also need to label its y-intercept. So y-intercept is here. You can just label a -4 here, right? So these are all the important elements: x-intercepts, y-intercepts, and behavior, right? You need to clearly state all the elements in the graph. Okay, so now let's do a practice. Sketch a graph of y equals -2x plus 1 to the power of 3 times x minus 3. I'll give you 2 minutes to think about it, okay? All right, let's try to solve this question all together, okay? All right, to solve this to sketch this graph, we need to analyze all the key features. First, degree, and then leading coefficient, and then end behavior, and zeros with degrees, and then y-intercept, right? So what is the degree? Degree is the highest order. Highest order, there are 3x here and 1x here, so the degree is 4, right? And leading coefficient. Okay, if you multiply all the 2x here, you will get 8x cubed, right? And multiply with this x, you will get 8x to the power of 4, and there is a minus sign in front. So the leading coefficient is -8, right? So end behavior. All right, if the degree is 4, that means this function is having either this pattern or this pattern, right? For an even number degree. And note that the leading coefficient is negative, so the pattern should look like this, right? Extending from the third to the fourth quadrant. Zeros. Okay, one of the zeros is minus x equals minus 1/2 with a degree with order of 3, right? And another zero is x being 3 with an order 1, right? For intercept, when x is 0, y is minus 1 times minus 3, which is 3, right? So the y-intercept is 0, 3. Okay, so now based on these information, we can sketch its graph. So first of all, we know that there are two zeros. One of the zeros is minus 1/2. The other one is 3, right? And this function should have any behavior like this, extending here and extending here, right? So when the function reaches this value here, because minus 1/2 has an odd order. Odd order, this function should change sign, so it will cross this point here, right? And all the way down to the other zero. And note that x being 3 also has an odd number. So this function changes sign at this point. So it crosses like this, right? So basically this function will have a pattern like this. And note that the y-axis should be here, right? This is our y, this is our x. And this point here is the y-intercept, right? Which is 0, 3. Okay, so basically this is a sketch of such a function. Okay, a nicer solution is illustrated here. You can read it after the class, okay? As you can see here, the graph of this function is basically the same with what we have drafted in our previous slide. All right, let's see the next aspect. The next key point is how do we write an expression for a polynomial function given its graph? So usually that involves 4 steps. First one is to identify the x-intercepts of the graph to find the factors of the polynomials. Second, examine the behavior of the graph at the x-intercepts to determine the multiplicity of each factor. Find the polynomial of least degree containing all of the factors found in the previous step. And then last, use any other point on the graph to determine the stretch factor. Usually the y-intercept might be the easiest. Okay, let's use an example to illustrate these methods. For example, given a graph like this, please write the formula for the polynomial function shown below. So how do we write the polynomial function given such a graph? First of all, we find zeros. Okay, note that when x is minus 3, y is 0, right? So this is one of the zeros. There is another 0 here and another 0 here, right? That means x plus 3 and x minus 2 and x minus 5 must be factors of the polynomial function, right? Next, we need to consider their orders. Note that when x is 3, the function changes sign, right? So at this 0, it should have an odd number order, right? So we can just use the least order, for example, 1, right? Of course, you can put a 3 here, but it asks you to write a formula, not a specific formula. So in order to keep it simple, usually we'll specify the least power, which is least possible power, which is 1, right? 1 is sufficient. Okay, the second 0 has a power of an even number, right? Because the function does not change sign here. The least possible number of order is 2, because 2 is the least possible even number, right? So we can put the power of 2 here. And the third 0 here, the function changes sign here. So this 0 has a odd number order, which we can put 1, because 1 is the least possible odd number, right? So basically, this function has these factors. And we can also put a stretch factor a, which is undetermined, in front of the function, right? So basically, we can write the function like this now. A times x plus 3 times x minus 2 to the second and x minus 5, right? And here we need to determine the value of a. Usually we'll use easiest point, which can be the y-intercept, right? So because when x is 0, y is minus 2. This means a times 0 plus 3 times 0 minus 2 to the second, 0 minus 5 equals minus 2, right? And this will give us a times 3 times 4 times minus 5 is minus 2, right? And this means a times 1 over 60 minus 1 over 60 is minus 2, right? Sorry. This means a times minus 60 is minus 2. So a equals 1 over 30, right? So the expression of the function is y equals 1 over 30 times x plus 3, x minus 2 to the second, and x minus 5, right? You understand? Okay, so now let's do a practice. This time, you need to solve this question by yourself. I'll give you 1 minute to think about it, okay? Write a formula for the polynomial functions shown below. All right, have you finished? How do we write the formula? Okay, note that there are 3 zeros, right? One of the 0 is -2, so x plus 2 must be one of the factors. Next, x minus 2 must be one of the factors, and then x minus 4 must be one of the factors because 2 and 4 are also zeros, right? Then let's consider the orders of such zeros. So note that the sign here does not change. So x plus 2 must have a order of even number. So smallest even number is 2, so we can put a 2 here. And for the other 2 zeros, the function changes sign. So we can just put a least odd number, for example, 1, right? Okay, remember there is a stretch factor in front of it, right? So this is a possible function, a possible formula for the function, right? Next, we need to consider the value of a. So note that when x is 0, y is 2. We can put this into the function, which means y equals a times 2 to the power of 2 times -2 times -4, right? Which is 2. So this means a times 4 times 8 is 2, which means a is 1/16, right? So the function is y equals 1/16 plus all the multiplied all the factors, all the other factors, right? Okay, so the final solution is y could be 1/16 times x plus 2 squared times x minus 2 times x minus 4, right? All right, now you should be able to find one of the equations given a function like given a graph like this. Okay, next let's have a look at how do we analyze the symmetry of a given polynomial function. So let's review the definition of even or odd functions. A function f is even if and only if fx equals fx for all x in the domain of x. An even function is symmetric about the y-axis. For example, y equals x squared, right? So this is a typical even function, which is symmetric about y-axis. On the contrary, a graph f is odd if and only if fx, f minus x equals minus fx for all x in the domain of f. An odd function is rotationally symmetric about the origin. Okay, for example, y equals x cubed. This is a typical odd function which has a graph like this, right? It is rotationally symmetric about the origin. Okay, this applies to polynomial functions as well. So let's do some practice. Without graphing, determine if each of the following polynomial function has line symmetry about the y-axis, point symmetry about the origin, or neither. Okay, I'll give you 1 minute to think about this question. All right, let's have a look at the solutions. So to check if this function is even or odd, we need to check that for all x belongs to the domain we need to check f minus x, right? For the first one, f minus x is 2 times minus x to the fourth minus 5 minus x to the second plus 4, which is 2 times x to the power 4 plus, minus 5x squared plus 4, which is actually fx, right? So f minus x equals fx. So this function is an even function. Even function is symmetric about y-axis, right? Okay, next one, f minus x equals minus 3 times minus x to the fifth plus 9 times minus x to the third plus 2 times minus x, which is 3x5 plus, minus 9x to the third minus 2x, which is actually minus fx, right? So this function is an odd function. Next, if we check f minus x, this is actually not equal to either fx nor minus fx, right? So this function is neither even or not odd. All right, next function. Also, if you check fx, this function, fx does not equal fx or minus fx. So this function is also neither even nor odd. Okay? You understand? All right, let's have a look at the next key point, families of polynomial functions. Okay, first of all, let's have a look at the concept and features. A family of functions is a set of functions that have the same characteristics. Polynomial functions with the same zeros are said to belong to the same family. The graphs of polynomial functions that belong to the same family have the same intercepts, but have different y-intercepts unless 0 is one of the x-intercepts. An equation for the family of polynomial functions with zeros x1, x2, xn is y equals a stretching factor a times x, the difference between x and x1 raised to the power of p1, etc., all the way down to x minus xn raised to the power of pn, where a belongs to a real number set, and a is not 0. And note that all the zeros here are different. And pi is called the order of x of 0 at x equals xi. Okay, that means, first of all, we need to simplify this and combining all the zeros in one factor, right? That 0 might have a 0 of pi. Okay, in this course, pi is 1 by default, unless stated elsewhere. An equation for the particular member of a family of polynomial functions can be determined if a point on the graph is known. Okay, I'll set you an example of this. So let's have a look at an example. For set A, this is a family of polynomial functions with zeros x equals 1 and x equals minus 2, right? So you can, as you can see here, all the graphs crosses the two zeros, and they might have different y-intercepts. And for the set B, actually, this is a family of polynomial functions that also have the zeros 1 and -2, right? But this time the stretching factor is negative. So these functions are opening downwards. Actually, all of these functions belong to the same family, which has zeros at x being 1 and x being -2. Understand? All right, let's see another example. The zeros of family of cube functions are 2, 1, 3. Determine an equation for this family, and then determine an equation for the number of families whose graph has a y-intercept 0, 15. Sketch the graph of the function obtained in part B. Okay, so how do we approach this problem? First, we can start with their zeros, right? Because they have zeros 2, 1, and 3, then x minus 2 and x minus 1 and x minus 3 must be the factors of this function, right? Understand? And because this function is a cubic function, so the highest order must be 3. So we don't need to put any other orders. You can just use order 1, right? Because order 1 times order 1 times order 1, you will have a cubic function. And you can also put a stretching factor in front of the expressions. Suppose this is a expression of the function. So this is an equation of the family of the cubic function, right? And then we know that this function passes through the point 0, 15. So when x is 0, y is 15. So this gives a chance to solve for a. When x is 0, that means a times -2 times -1 times -3 is 15, right? So a is 15 over -6, which is -2 over 5, right? Okay, so the function is y equals -5 over 2, x minus 2, x minus 1, x minus 3, right? Next, we can sketch this function. First of all, you can label the zeros first. Zeros are 3, 2, 1, right? And the end behavior, because this function has a degree of 3, 3 has a pattern like this or this. And then the leading coefficient is negative, so the function must have a pattern like this. So extends here, right? And note that all of the zeros has a degree of 1. So the function here changes sign, right? So basically the function have a pattern like this. It changes sign at each of the zeros, right? Okay. All right, next let's do a practice. This time you need to solve it by yourself. I'll give you 1 minute to think about this, okay? All right, let's have a look how to do this. Okay, we know that the polynomial functions has zeros 2, 5, and -1, and -1 has order of 2, right? So we want to determine an expression. Okay, so with these zeros, the function must have a factor of x minus 2 and x minus 5 and x minus 1, x minus minus 1, which is x plus 1, right? Okay, and x plus 1 has an order of 2, and also we need to put the stretching factor a in front of it. So basically this function has an expression like this, right? And then we need to solve the factor of a here. We know that passing through 1 minus 48, so that means when x is 1, y is minus 48. This gives us a times -1 times -4 times 2 to the power of 2 is 4, which is minus 48, right? So a is minus 48 over 16, which is minus 3, right? So the function is y equals minus 3 times x minus 2 times x minus 5 times x plus 1 to the second. Okay? All right, again, a nicer writing of the solutions is illustrated here. You can check it after the class, okay? All right, let's do another practice. Here, you are given a graph of a polynomial function. Determine an equation for the polynomial function represented by the following graph. Okay, I'll give you 1 minute to think about it. All right, let's have a look at the solution. So first of all, let's start with all the zeros. We have 1, 2, 3, 4 zeros, right? One of the zeros is x equals -3. So that means x plus 3 must be a factor, right? Next, the function has a zero of x being -1/2, right? So that means 2x plus 1 must be a 0, right? And note that the 2 zeros here, the function does change sign at the 2 zeros here. So we can just use the least possible odd number 1 here, right? Both of them has an order 1, which is an odd number, where the function changes sign. Next, the 0 of x being 1, so that means x minus 1 is also a factor. So note that function changes sign, right? If the function changes sign here, it has an odd order, which we can use the least order 1. Next, x being 2 is 0, so x minus 2 must be a factor, right? Also, the function changes sign here. If a function changes sign here, the order here is an odd number. We can use the least odd number 1, right? So after that, we can put a stretching factor a in front. So basically, this function has a form y equals a times x plus 3, 2x plus 1, x minus 1, and x minus 2, right? And in order to find a, we need to use a point on the graph, right? So usually we can use y-intercept, which is when x is 0, y is 3, right? This means a times 3 times 1 times -1 times -2 is 3. So that gives us a is actually 0.5, right? So the final solution is y equals 0.5 times these factors. This could be a possible solution to the graph, right? Note there should be a lot of solutions. The function here we find is the function with the least degree, right? Okay, again, here is a nice writing of the final solution. You can check it after the class, okay? All right, let's make a summary of today's lesson. So now you should be able to understand the definition of polynomial functions and related terms such as degree, leading coefficient, constant, zeros, orders of zeros, and global optimum, local optimum, etc. And you should also be able to determine if a given function is a polynomial function. Also, you should be able to understand key features of the graph of polynomial functions. Sketch the corresponding graph given the expression of a polynomial function, and write an expression for the polynomial function given its graph, and write an expression for a polynomial function given its zeros with orders and a point on the graph. And last, you should be able to analyze the symmetry of a given polynomial function. Okay, so that's all for today. I'll see you tomorrow. And please remember to complete and submit your homework on time onto Google Classroom. Okay.